Hi, in this video we're going to work on a finite state machine design of an elevator. We're going to create an FSM to simulate a freight elevator for 2 floors. It has a single set of call buttons and they can be operated from any floor or inside of the elevator. So we have 2 inputs, up and down, U and D. We have as outputs, we're going to have 4 LEDs, 2 yellow LEDs to indicate the current floor, a green LED to indicate if the elevator door is open, and a red LED to indicate when the elevator door is closed. So details are that the elevator can only move up and down with the door closed, and also the elevator can only open the door after it has first stopped at a floor with the door closed. More details are that if no buttons are pushed, the elevator stops and then it opens the door. If the elevator was already open, the elevator should stay as it is. If the down button is pushed, then the elevator should close the door and then move down 1 floor. If the elevator reaches the bottom floor, it should stop and not open the door until the button is released. Now, if the up button is pushed, it has a similar behavior as the down. When the elevator it stops first and then it closes the door and then it moves up 1 floor. If the elevator reaches the top floor, then it should stop and not open the door until the button is released. If both buttons are pushed at once, the elevator is going to freeze without changing the floor or the state of the door. So if we see the design steps, the first one is to draw a state diagram. In this case, we're going to work on a Moore machine. The second step is to get a state table from the state diagram. The third step is to have the state assignment and create a state assigned table. Then we're going to derive the output logic. We're going to choose the flip-flops and create a flip-flop input table. And finally, we're going to derive the input logic. So we start with the state diagram. And as in a previous video, we need to start from a first state, that is where or when our system is going to be first power on, or if we press a reset signal. Okay, and we need to think about the initial value of the output or outputs. At each of the states, we need to consider all the possible input value combinations and also what the circuit should do for each of these combinations. Also, we can add states as needed. So we're going to start with a first floor and the door is closed. So we're going to call it 1C, and we're going to think about the outputs, but we're going to leave that for the next slide. Okay. Then we're going to look at the possible input value combinations, which are what? We have U and D, right? And so we have a 0, 0, 0, 1, 1, 0, and a 1, 1. So we need to look at each of these. So it says that whenever actually I have it in the next slide. Let me see. We start this. Okay, so here are the details. So we're starting again from the 1C, and then we're gonna look at the combination. So I have U and D, and so I have 0, 0, 0, 1, 1, 0, and 1, 1. And we're gonna look at each of these. So button operation, that means I have a 0, 0. No buttons are pushed. The elevator should stop if it was moving and then open the door. So in the first case, we're going to go with another state. Actually, I wanted that in red. We're gonna look at 0, 0. We're gonna make another state because in this left state, the door is closed. So this one is 1, but it's open now. So that's for our 0, 0, 0, 0. Now that's for this one. Now 0, 1. That means that we're pressing the D button, the down button. So down button, let's do that green, down button. The elevator should close if the door was open, and then move down 1 floor. But we are already in the first floor. If the elevator reaches the bottom floor, which is our case, it should stop but not open the door until the button is released. So it stops here, it doesn't go further down, we don't have another floor. It's just going to stay there. That's a 0, 1 until the button is released, which is our 0, 0. Now, what about the 1, 0? So 1, 0, that's up button. And it says the elevator should close the door if it's open. And remember, we're working on the 1C, which is the first floor close. So elevator should close if the door is open. We're in the closed state, and then move up 1 floor. Okay, so now we're saying that it needs to move up 1 floor. So we're gonna go up 1 floor. That's our 1, 0. And we're going to put A. So now we're in the second floor and the door is still closed, okay? Now the last state, we put that purple. The last state, it says that 1, 1. So both of the buttons are pressed. It says the elevator should freeze without changing the state. So we're just gonna state in that case. So 1, 1. Okay, so we went through all of the possible combinations for the inputs that we have. And at each of these, you have to go slowly thinking what it does whenever I press the down button, whenever I press the up button, when I don't press anything, or when I press both. So now that we have that, you can kind of get an idea of how this is going to look like. We have first floor closed, we have first floor open. Now, I think we're gonna also have a second floor open, if you can kind of think from the process that we have been doing right now. Now, the other thing is that at each of these states, we're gonna have 4 arrows coming out of it. We can go about this in 2 cases, and you can also do this for any design. You can go by state. So we finish this state, we can kind of figure out all the possible combinations coming out of this state. Or if it's easier, which sometimes it is, we go by combination. So for example, if I look at the 0, 0, actually the 1, 1 is even easier. The 1, 1, it says that the elevator doesn't change. So I know that whenever the 1, 1 is pressed, it's just going to stay there. So that's my 1, 1. And so that's my 1, 1, right? It says that that's what it says, the 1, 1. So yeah, we eliminated all of the 1, 1s. Similar case with the 0, 0. It says that the elevator should stop and then open the door. And if the door was already open, it stays like that. So it's saying that if it's closed, it should open. So I go do this one. And if it's open, it stays the same. So I go do this one too. So 0, 0. And now you can see that I have 1, 2, 3, 4, 1, 2, 3, and 4 of my combinations. So each of these states we already counted all the 0, 0s. Now, what about which one I got? The green one, 0, 1. So let's do 0, 1. That means the down button is pushed. So it says the elevator should close. So if I'm in the open, it's gonna close it. So that's our 0, 1. If I'm in the elevator should close if the door is open. So whenever the door is open, I close it. Okay, so that's our 0, 1. If the elevator reaches it, I'm sorry, going back to the same one, elevator should close, then move down 1 floor. Okay, so in the case of the second floor, it's gonna go move down. What else I'm missing? Already got this one, I already got this one, I also got this one, and I got this one. So I think we're done. It just goes down, right? If it reaches the bottom floor, it stays there. So what about the last one, which is the purple? Similar case. If the up button is pushed, the elevator should close and then move up. Okay, so we're going to do the purple ones, and so we're going to close the door. We're going to close the door. We're going to move up one floor, and also if it reaches the top floor, it just stays there. So we're gonna do this, and that's the 1 0. Okay, so you can go in two ways. You can go by stage, sometimes by state. I'm sorry, by state, or you can go by input combination, drawing your input combination in all of the diagrams, in all of the states. Okay, so now we have that one. What is next? We're gonna look at the state table. So the state table is just another way of visualizing the behavior of the machine. And in this case, we said we have a one open, one close, two open, and two close, right? And now let's look at the outputs at this moment. The yellow LEDs were going to indicate to us what floor. So if I'm in the first floor, I say, well, I'm in the first floor. If I'm in the first floor, I turn on the yellow one. If I'm in the second floor, I turn on the second floor. Now for the green and the red. The green means that the door is open. So if the door is open, I turn on the green LED. If the door is closed, I turn on the red LED. And so that's it with our outputs. Now, this section, the next state, we're going to take it from the diagram, okay? So let's do this one. So 0, 0, and I'm at the open state, and I just remain in my first floor open. If I'm in the one close, first floor and close, and I don't press anything, it should open, right? So one open. Now same thing. If I'm in the two open, I don't press anything, so I stay two open. And if I'm in the second floor and it's closed and I don't press anything, it should open also the door. Okay, so I'm kind of thinking and at the same time following from whatever we derived already. Now the 0, 1. I'm just gonna copy it from the one open. 0, 1 goes to 1C. If I'm in 1C and I press a 0, 1, where's my 0, 1? It stays the same. If I'm in the 2 open and I press 0, 1, I go to 2C. If I'm in 2C and I press 0, 1, it goes to 1C. Now we can go down or we can go right. Sometimes it's easier. So if I'm 1 in 1C, I'm going to be pressing the 1, 0, so I go to 1C. If I press a 1, 1, I stay in 1, 0. Actually, the 1, 1, remember the 1, 1, it happens that it stays in the same one, so that one's easy to see. Now this one, I'm in 1C, and I press a 1, 0, I go to 2C. If I'm in 2 open, and I press the 1, 0, I go to 2C as well. And this one I'm in 2C, I press the up button, I remain in 2C. Okay, so something like that. So now we need to assign states to each of we need to assign values, specific binary values to our states, okay, to each of our states. Remember that we said that whenever we have 2 variables, we can have 4 values. Whenever we have 3 variables, we can have 8 values. In this case, we have 4 states, right? And so we need 2 variables, Q1 and Q0. That will be 2 flip-flops. So this is our schematic. It's taking shape. I have 2 flip-flops now in the middle. If you also look at the right hand side, we're going to have 4 outputs coming out of our output logic circuit, and we have 2 primary inputs. If you think about this one, is actually this is all our finite state machine, okay, that has two inputs to it, the U and the D. Let me see if I can erase these so it looks a little bit better. So I have U and I have D, and coming out of it I have yellow 1, yellow 2, green, and red. Whatever intermediate steps I use here and here and here and here, this will have internal inputs, internal outputs, inputs and output, but the final output is all the way to the end. The primary inputs are all the way to the left, okay? So now that we decided, or we figured out how many flip-flops we need, we can assign values to each of these. So I'm going to assign, I always say 0, 0, 0, 1, 1, 0, and 1, 1. And I usually like to follow this order because it becomes easier when doing each of the tables. If you could also say, you know what, I'm going to do a, how can we call it? I'm going to do a, the first value is going to be open, and that's first floor, and then that's open, and that's second floor, or actually you can say that's open and that is second floor, and then you can say close is my 1 and that's close. So I've kind of flipped the variables, and you can do any order, okay, any assignment. You can even say this one is 1 1, this one is 0 1, this one is 0 0 1 0, any order that you prefer. The only problem will be at the end, or whenever you are doing truth tables, you have to kind of follow the 0 0 0 1 1 0 1 1 order. So it's just one extra step if you do it in a different way, but it can be done. So now the state assigned table with our state table and with the assignment table, we can combine those two and we can create the state assigned table. So now I'm going to recopy these, but instead of using a 1 0, I'm going to use a 0 0. Instead of using a 1 C, I'm going to be using 0 1 and so on. So I'm going to do that. 0 0 0 1 1 0 and 1 1. And then so we said 1 0, so that's 0 0, 1 0 0 0, 2 0 2 0, that is 2 0, that's 1 1 0 and 1 0. So now this one 1 C 1 C, so that is 0 1 0 1 0 1, 2 C 1 1, and then 1 C again, so that's 0 1 again. Okay, what else? We're going to go to the next column. 1 C, which is 0 1, and then 2 C 2 C 2 C, which is 1 1. Last one, this one, it follows the same order of this, right? And we said 0 0 0 1 1 0 1 1. In the case of the output, remember we had first floor, second floor, second floor. And then we had open, and then this one was close, open, and close. Okay, so that's it. We just have to rewrite the we have to rewrite the state table using the assignments now. The next step is to derive the output logic. So in that case, we're going to ignore the columns in the middle of the previous table. And we're just going to look at the current state, because that's what the more does, right? We're looking at the current state and the outputs. And so you can think about these as a like several truth tables, or a truth table with 1, 2, 3, 4 outputs. So in the case of y1, what is y1? Can you see that is following q1? So I have 0, 0, 0, 0, 1, 1. This one I have 1, 1, 0, 0. So it's actually opposite. So q1 not. What about the y2? Y2 is following q1. What about the case of the green, for example, or the red? So let's do the red. The red is R is equal to 0, 1, 0, 1. Can you kind of see that is Q0? So it's following Q0. In the case of Q1 in the case of the green LED, that's going to be Q0 not. So opposite. We can also use K-maps for this. For example, if we do the Y1, and it's a two variables, so 0, 1, 0, 1, Q1, Q0. So we're going to do 1, 1, 0, 0. So what does that give us? This gives us just Q1 not. So Y1 is equal to Q1 not. And actually this doesn't look like a Y, it looks like an X, so Y1. And so you can do the same for each of the output variables. So now you can draw actually this whole circuit with using the gates. Or actually just directly, right? This one is just going to be connected. The Q1 is going to be connected to the Y2. Let me just do that one. I wanted to write it, but this one means that Y2 is connected to Q1, so it's this with this one, right? And then we have, for example, Q1 not. That's our this guy, and so on. You get the idea. We don't have gates in the output block. Because why? Because our outputs were very simple. So now we need to choose flip-flops. In this example, we're going to work on a D flip-flop. We're going to use a D flip-flop. In the next example, in a separate video, we're going to use the JK flip-flops. So why D flip-flops? Because it's straightforward, it's easier. You do end up with a flip-flop input table that is easy to do. However, the actual circuit or the function, the equations of the circuit, it's going to be more complex than if you use JK. Okay, so I'll explain that difference in the next video. So now we decided D flip-flops. Okay, we need to think about the flip-flop input table. What is the flip-flop input table? The flip-flop input table, we make it so that it tells us what do we need to put at this input so I can make my Q plus, my next Q, the one that I need, right? So what do I need to put here so that a Q plus is whatever I want? So in this case, since it's a D flip-flop, whatever I want to see at the output, I need to put it at the input. So if I want to see a 1 at the output, I put a 1 at the input. If I want to see a red at the output, I put a 0, I put a 0 at the input. So that's why the D table is easier because whatever I want to see, for example, Q1 plus, this one, for example, if I want to see a 0, what do I have to put at the input? A 0. So I just write it here. If I want to see a 0, I write a 0 at the input of the D. If I want to see a 0, I write a 0. If I want to see a 1, I put a 1 in my D flip-flop. And so that's the idea with the D flip-flop, that we just copy our, this is actually the state assign table. And so we just copied that one into the flip-flop input table. So I'm just going to copy that one straight. These are the same values, 0, 0, and so on. Actually, I forgot to say that we don't even need the output columns anymore. We just need this state assign table, and we copied the values there. So there you go. There you go. So I recommend you to kind of stop the video and try to see if you are following up, and before I give you the final answer, for example, for the table, for each of the tables that we're doing. Whenever I work on something, I usually work on 1, 2, 3 sets, for example, and you can pause and then finish up the table, and then you can compare my final table with your final table. Sorry. So this is how it's going to look like now. So we had mentioned that we have this, we have that. Now we need to think about this input logic circuit. This one, it needs what? It needs U and D, and it also needs Q1 and Q0 as inputs, and it's going to give as outputs, it's going to give us D and D0. Okay, so we need to think about a logic circuit that we design that has these inputs and these outputs. Okay, we're going to see now. Okay, so here we have the same table, the flip-flop input table, and I color-coded it white. You're going to see why in a minute. We need to think about this one having inputs UD and Q1 and Q0, right? I just said that in the previous slide. And it's going to produce D and D0, D1 and D0 as outputs. So you need to think about this as a regular truth table like you did in digital class. So how do we convert that into our truth table? It will be like this. You have the red values, you have the blue values, yellow, and then you have the orange values. And so you need to think about this. You can do this because I take Q and D as inputs, take Q and 0 as inputs, and I organize them such that U and D, my primary inputs, are the most significant bits here. And so I recommend you always doing that. That way you can grab by column and directly put it like that. The next 4 is the next 4. You can kind of see, right? This is 0, 0, so it corresponds to this first in a true table. The top 4. The next 0, 1, you can kind of see it corresponds to the next 4 in the true table. See, it's all 0, 1, 0, 1, 0, 1, 0, 1, and so on. So we're kind of like dividing like that and like that. If you do opposite, if you do Q1 first, Q0, and then UD, you have to go in what direction do you have to go? You will probably have to go in this direction, okay? So it will be color coded different, okay? If you do the Q1, Q0, U, and D, okay? It can be done, just have to know what you're doing and be careful so you can fill it out like that in there, right? For our example, we're just gonna do this way. So what's next, right? So these you have done in previous classes. You can use multiplexers, you can use K-maps or any other, like an encoder or any type of logic circuit that you want to design. Let's just do, just for practice, we're going to do a K-map. So we're going to do D1 1 0, no, it's 1 1. And that's U D Q1 Q0. So this is going to be the, so I have a 0 0 1 1. So I have a 0 0 1 1 0 0 1 0 0 1 1 1 0 1 1 1 0 0 1 1 0 0 1 1. Okay. Now how do you circle this? So I will probably do these 4, then I would do these 4, then these 2 with this one, just to what? Just to get this guy, and then which guy we're missing? We're missing this last one right here. So this one we're gonna get with this. So now this case will be U D naught Q0, right? What else? If we do the green one, we're going to have this and this one, which is the U, and then this one and this one, which is the Q1. Just double checking. 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. Okay, and then I have this guy, which is Q1 Q0 not. Last one, the purple. This I have looking at this guy and looking at this guy, so that's a D naught, and then I'm looking again at this and this, which is the Q1. Okay, so, and remember this is all OR, right? So I have D1 is equal to Q1 Q0 naught, or D naught Q1, or U Q1, or U D naught Q0. So finally we have our diagram, and this is not a complete diagram, right? Because for a complete diagram schematic, I would have to go draw these with actual gates, and these just have it connected. Okay, but you have an idea that you have to implement these equations on this side, you have to implement these equations on the right hand side, and that will be the final. Okay, or like this. So left hand side, this is all going to be the input circuit block, and all of these will be just connected directly, right? Like I was saying, connect this directly to this guy, and so on. Okay, so that's all I got for this example. In this video, we're going to look at the same problem, but now we're going to use JK flip-flops, but that's going to be in a separate video.